default record option. I was looking at this setting and I couldn't find the default recording option. Anyway, yeah, so we are looking at derivatives. So the derivative at an interior point C is defined as f prime at C is equals to limit h tending to 0 f at C plus h minus f at C upon h. Right. So let us consider any point C and take a point C plus h. So this is your f of C and this is your f of C plus h. So this thing in the box, f of C plus h minus f of C upon h, is basically this height upon this base, because this height is your numerator, right? And this base is C plus h minus C, so that is your denominator. So what we are basically looking at is the slope of the line segment which will join these points. And what does the limit do? The limit says that what happens to this slope as you pull this point towards the point C. Okay, so I'm going to reduce the distance between these 2 points. I'm going to reduce this distance between the points h to 0. So this h is going to go towards 0, and then I'm going to look at what happens to the slope m of this line segment. Now, it's basically slope. Okay, so f prime C is basically the slope of the function f of x at C. Okay, so at this point C, if you were to draw tangent to this particular curve, okay, it would look like this, something like this. The tangent would look something like this, and the slope of the tangent is going to be f prime at C. Okay, so it is a slope. And what is a slope? A slope is basically rate of change. Okay, slope is rate of change. But change of what? Rate of change of f of x with respect to x. Okay, so x is some variable which is affecting the function f, and I'm looking at how does this functional value changes with respect to x. So suppose I have utility of just one variable. Suppose I have utility of a single good that I'm consuming ux, which is let's say 100 minus x square minus 10x minus x squared. Okay, so I want to optimize this function. I want to find at what value of x is this thing going to be its maximum. Okay, so I'm interested in finding out at what value can I maximize this function u of x. So as you can see, this u of x function, it changes as x changes. So when I'm talking about f prime of x, or u prime of x for that matter right now, u prime of x, this is going to be u prime at C, sorry, u prime at some particular value C. This is going to be the rate of change in utility with respect to consumption, of good x. So how does utility change with respect to x? That's what I'll be looking at. Okay. Now it applies to all sorts of functions, but I will be particularly interested in utility functions because I'm looking for the scope of this particular derivatives in economics. So my examples would time and again come back to revolve around utilities and profits, but its scope is in general true. So physicists apply it for different reasons. So I don't know if you have done the projectile motion thing, that how does the range of the projectile change with respect to the angle that you throw it in. So if you if you have done it, maybe you if you have had physics in your 11th 12th, maybe you would have done that. So the scope is pretty wide. We are going to look at the scope in this particular chapter, and then in all subsequent chapters in microeconomics we are going to keep applying it again and again. So that's your f prime of c. Now this definition is very, very important. You need to remember it. You'll see multiple past year questions which are based on this definition. Even this year ISI has asked one question which is based on this definition. Another way to write this would be f prime c is limit x tending to c f of x minus f of c upon x minus c. So now what's happening is, this is your function. They take the point c, they take another point x, and then they move this point x towards c. Okay, so he's doing the same thing, but instead of calling this point c plus h, he's calling this point a different entity altogether, x. And then instead of making this distance h0, he's taking the limit that x tends to c. So this is another definition, not that popular. The first definition is the one which is mostly used in text these days. Now, differentiability and continuity. So if f a to b is differentiable, then f is continuous at c. So this is important theorem. It says that if a function is differentiable, then it is definitely continuous at that particular point. So the proof is very straightforward. How do we prove this? So remember the first chapter, we did some basic ideas about proofs. Okay, so one way to do this would be a direct proof. So here what the strategy that we are applying is, we have to show that differentiability implies continuity. So we assume that the function is differentiable. So we apply the definition of differentiability at c. So we say that limit f of, we say that this particular thing minus f of c. Okay, so limit f of c plus h minus f of c. So this should be equal to limit of f of c plus h minus c. We multiply and divide with respect to h. And then we say that this particular thing is f prime of c. So f prime of c into 0. Now, if the function is differentiable, then this f prime of c, it is a finite entity. So something finite into something 0 is going to be 0. So what we have essentially shown is that as h tends to 0, f of c plus h and f of c are same. So we have essentially shown that limit h tending to 0, f of c plus h minus f of c, this entity is equal to 0. Sorry, yeah, minus f of c, this entity is equal to 0. So f of c plus h is equals to f of c. So the function is basically continuous. So this is a direct proof. Another way to do the same proof, just for some mental exercise, would be an indirect proof. So let's try to build an indirect proof. So suppose I want to show differentiability implies continuity. Okay, so this thing, so I can start with a function that is, I'm saying that in the class of all differentiable functions, this is the class of all continuous functions. So the set of differentiable functions is a subset of all the continuous functions. So to disprove that, I will take a differential function. I'll say that let there exist a function f of x, which is not differentiable but continuous. No, sorry, not continuous but differentiable. Okay, so I'm saying that there is some function which lies inside D, but not inside C. Okay, so here the graph clearly says that all functions which are differentiable must be continuous. I say that assume that there's a function which is inside D, but not inside C. So I'm saying that maybe the set D looks something like this, and you take a function here, F. Okay, so it is not continuous. It is not continuous. So if it is not continuous, then I can be sure that limit h tending to 0, limit h tending to 0, f of c plus h, this cannot be equal to f of c. Okay, so this is the definition of continuity, right? Because the definition of, sorry, not continuous, not non-continuity. Because the definition of continuity is this thing. This thing implies continuity. So if I put a not equal to sign here, this becomes non-continuous. So now this function f is non-continuous. Now let us look at the differentiable part. So since it is differentiable, f prime at c must be equal to limit h tending to 0, f of c plus h minus f of c upon h. Now, since these two entities are different, they are not equal, let me call this thing a value k. So this becomes equal to k minus f of c divided by limit h tending to 0, h. Now the numerator is finite, but the denominator is tending to 0. So this thing basically will tend to infinity. So f prime c does not exist. So if you take a function which is not continuous, so the the moral of the story is that if f is not continuous, then f is not differentiable. Now, why this takes precedence is that sometimes questions, they give you a function is differentiable. So they might not tell you that it is continuous, but continuity is implied. There cannot be a function which is differentiable but not continuous. But there are functions which are continuous but not differentiable. Okay, so I'm saying that there are no functions which are differentiable but not continuous, but there are certain classes of functions, let's say g of x here, which is continuous but not differentiable. So can you give me an example for a function that is continuous but not differentiable? Maybe you would have read it somewhere. I have not introduced it yet, but maybe you would have read it somewhere. Okay, so we'll come back to that when we look at differentiability of the function, because right now we have only looked at differentiability at a point. Next is continuously differentiable. Continuously differentiable is not continuous and differentiable. Okay, it is not continuous and differentiable. It's a completely different, not completely different, but it is a different thing. Continuously differentiable is something more stricter than just differentiable, because differentiability automatically implies continuity. Okay, so once you say differentiability, you don't need to say that it is also continuous. That's not necessary. So let's look at this definition of continuously differentiable. The reason you need to know this is this definition comes up a lot in past year papers. So what is a continuously differentiable function? So a function f is continuously differentiable if it is differentiable and f prime is continuous. Okay, so f prime should be continuous. So let us look at this function x square sine 1 by x. Now I've not defined all the rules of differentiability right now, but I'm guessing that you guys would know it. If you don't remember it, maybe you'll be able to appreciate this example later on. But let's look at what this functions, is this function continuously differentiable or not? So let us look at f prime of x. So f prime of x is going to be equal to 2x sine 1 by x plus x square cos 1 by x minus 1 by x square. So this becomes negative. So this is 2x sine 1 by x minus cos 1 by x. Okay. So this is my f prime of x. Let us look at how to check for differentiability of f of x. So obviously f of x is differentiable at all the other points. I just need to check for differentiability at 0. So the aim is to check if f is differentiable at 0. Now for a function like this, you cannot rely on f prime to check for differentiability at 0, because this function is a piecewise function. Piecewise function. So the way to check for differentiability is the original definition. So limit h tending to 0, h square sine 1 by h minus 0, because f of 0 is 0, upon h. So this is going to be my f prime at 0. So what is f prime going to be? What is the value of f prime 0 going to be here?
0.
0, very good. So this becomes just limit h tending to 0, h sine 1 by h. Now 1 by h is going to oscillate between minus 1 and 1, but h goes to 0. So 0 multiplied by something which is finite is going to be 0. So f prime of 0 is 0, which means that f prime of 0 exists. Okay. So the function is differentiable. The function f is differentiable. So this part is checked. I have checked its differentiability. Now let's come to continuously differentiable. So my f prime of x is defined as this value for x not equals to 0. And it's defined as f prime of 0, which is equal to 0 at x equals to 0. So this is my complete definition of f prime of x. Now I want to check for the continuity of this guy. So tell me, what is the limit of this function? Let me ask this to Kritika. What is limit at x tending to 0? This part. 2x sine 1 by x minus cos 1 by x. What is going to be limit x tending to 0, this thing?
Is it -1?
Okay, let me break it down for you. What is the limit for this thing, Kritika? 2x sine 1 by x. Limit x tending to 0, 2x sine 1 by x.
It's sine infinity, right?
So, no. What is this thing? What is
That's
limit?
0.
So why is this thing something else? This is basically the
Yeah,
same.
that's
I
0.
replace h with x and you get confused. No, right? I mean, it should be 0. What happens to cos 1 by x? We did this in last class. What happens to cos 1 by x as x tends to 0? Can anybody else chip in? What happens to cos 1 by x? Come on, we did this in the last class. Nobody here knows what happens to cos 1 by x as x tends to 0. What is limit x tending to 0 cos 1 by x? What is this limit?
So between -1 to 1.
No, the limit does not exist. Limit has to be unique. It is not a range. Limit is not a range. That was one of the theorems we did. That limit, if it exists, is unique. You cannot give a range to the limit. So this limit does not exist. Okay, so f prime x limit will not exist because this thing is going to 0, whereas this thing is an oscillating function. I showed you this graph. Come on, guys. I mean, you have to work harder than this at least. You cannot mess up with things that we are learning in class. That is terrible. That is absolutely terrible. We did this thing. Okay, we did sine 1 by x. So I convert sine to cos, nothing changes, right? It is an oscillating function like this. It keeps oscillating and this limit does not exist. Okay, we did this graph. So you should be getting it. You should have got it. Anyway, so important thing is f prime x limit does not exist at 0. So f prime x is not continuous. Okay, so the important thing is that f is differentiable at 0, but f prime x is not continuous. So this function is not continuously differentiable. Okay, so a continuously differentiable function implies that the function is differentiable at function is differentiable plus its derivative is a continuous thing. Yeah. All right, let's look at chain rule. So the chain rule states that composition derivatives done. Yeah, okay. I should put these common derivatives first, probably. That would be better. Anyway, let's do these common derivatives and then circle back to chain rule and convexity, all those things. So let us find some common derivatives. Look at how differentiation works. So let's say the function is f equals to c x to power n. I want to find this derivative at any value x. So I want to find f prime at x. So this is going to be limit h tending to 0, f of, let's start with a simpler one. Let's say f of x equals to x squared. I want to find this. So f of c plus h or x plus h minus f of x upon h. So this is going to be limit h tending to 0. Now, instead of x square, what I'll get is x plus h whole square minus x square, because f of x is x square divided by h. So this is limit h tending to 0, 2x square plus 2hx plus 2h square minus x square upon h. Oh no, x square plus, yeah. So x square and x square cancel out. So you are left with limit h tending to 0, 2hx plus h square upon h. So let me ask this question to Manas. So Manas, what is going to be this limit? See, I ask questions, okay, because I want to know if you are with me or not. So,
So 0?
no, it's not 0. X is not 0, H is 0.
X is not 0. Yes, H is 0.
H is 0. Do you want to give another answer? So you have to break it up. You have to break it up. This becomes limit h tending to 0 to hx upon h plus limit h tending to 0 h square upon h. So let me break it up for you, Manas. What is going to be this limit? H tending to 0. Manas? Hello, Manas? Anyway, I can't wait forever. So this is going to be 2, h cancels out. So this is going to be 2x plus this becomes just limit h tending to 0h. So that is 0. So this becomes 2x. So that's how you get the differentiation of x square as 2x. Okay, so maybe you remember the formula for differentiation, that differentiation of x square is 2x. What you might not have remembered right now is how do we reach to that 2x? Okay, so that is crucial. Similarly, you apply the Taylor expansion, binomial expansion for any power n, and you get this particular differentiation. Now, the beauty about this differentiation is that it holds for any value of n, not just natural numbers. Any real value of n is applicable. So the exponent for x could be any real value. Okay, so why don't you guys just tell me quickly? Let me open up a document that I want you to read after this lecture. It's going to be on derivatives, but some basics of differentiation. So this is again uploaded, differentiation.pdf. So this has some basics, and then it has these sections. So derivative of a constant function. So constant function does not change. So its derivative is 0. Okay. Then, yeah, derivative of y equals to x to power n. So we look at differentiation of x to power n. Okay, so I want you to give me the differentiation for, let me see if there's any interesting example here. Yeah, root x, differentiation of root x. So that is x to power half. So y equals to x to power half. So the formula is that if y equals to c times x to power n, y prime, which is the differentiation, becomes cn times x to power n minus 1. So if this is my function y, what is going to be y prime?
1/2 root x.
1/2 root x, very good. Or so this is your n's. So it comes in the front, and the power becomes 1 less than whatever it was earlier. So this becomes half x to power minus half. Now x to power minus half is basically 1 by x to power half. So x to power half becomes root x. So 1/2 root x. So this is going to be by far the most important type of derivative that we are going to do, apart from the fact that constants don't have a the differentiation of constants is 0. So if your utility is basically some function 10xy, okay, I have not reached partial differentiation, so let's focus on single variable things. Some other differentiations which are very important: differentiation of sine x is cos x, differentiation of cos x is negative sine x. E to the power x remains unscathed, so it has the same differentiation. Log x becomes 1 by x. and a to power x. Okay, so x to power n and a to power x, focus on these two things. These are different. Here x is the base. Here x is the exponent. So when x becomes the power and you differentiate with respect to x, you get your differentiation as a to power x ln a. Okay, so this is something that people tend to forget. In the heat of the moment, you might like that write this differentiation as x a to power x minus 1, and it would be wrong, completely wrong. Okay, because you would have applied this formula instead of this formula. So don't do that. Notice where x is, what are you differentiating with respect to, because when things get complicated, you are going to have multiple function, multivariate functions which you will have to differentiate. So you have to keep an eye on what are you differentiating. So with that in mind, let's come back to what I skipped, that is chain rule. So chain rule states that the composition of differentiable functions is differentiable. Okay, so I know that x square is a differentiable function. So f of x equals to x square is a differentiable function. G of x equals to sine x is another differentiable function. Okay. So f of g of x is also going to be differentiable, and g of f of x is also going to be differentiable. So Vama, can you tell me what is going to be the composition f of g? Vama, somehow you guys just ignore me, right? It's not good. I'll stop asking questions, so you'll not learn. Okay, let me move to Vijay. Vijay, are you with me, Vijay?
Yes, sir.
Okay, can you tell me the composition f of g?
F of gx.
Yeah, f of g of x. What is
So it
this?
would be sine x whole square.
Very good. So it's going to be sine square of x. And Vinay, what's going to be g of x? Vinay,
Yeah, sir.
you guys should give me your phone numbers. Okay, I have your phone numbers. I'll call you next time. Okay, if you don't respond quickly. Yeah, what is g of f?
So it is g of sine x,
I don't want g.
sine x square.
Sine x square. Very good. Sine of x square. Okay, this is sine square of x and this is sine of x square. So both these functions are going to be differentiable. You don't need to check for the differentiability again for these two functions. What this theorem is saying that if you take two differentiable functions and you take a composition, this composition is going to be differentiable as well. Moreover, if f is differentiable at if f is differentiable at c and it scales lengths by a factor of f prime at c. So suppose I am interested in okay. So suppose I am interested in g of f for some functions. Forget this. Okay, so there's some function g of f of x. So I am interested in the derivative of this function. Okay, so what is the derivative of this function? The implication is how does g of f change as x changes? Okay, so what is the rate of change of g of f with respect to x? So that is what I'm interested in. So so first of all, so this theorem is saying that g of f prime of c is equals to g prime at f of c into f prime of c. So it's saying that g of f prime of x is equals to g of f prime at g prime at f of c. into f prime at. So let us break this down and see what's happening. So I want to see how g of f changes with respect to x. So what is the magnitude of change in g of f with respect to, let's say, 1 unit change in x? Okay. So g of f is g of f of x. So let's say f prime at c is 10. So for every 1 unit change in x, f of x is changing by 10 units. So if x changes by 1 unit, this is going to cause 10 unit change in f of c, right? And when this thing changes by 10 units, the input of g, which is f of x, has changed by 10 times. So that's why I'm multiplying this g prime f of c by this factor f prime of c. This factor is coming in because x is not affecting g directly. It is affecting g through f. So if I change x by 1 unit, I have changed the input for g by 10 units, or rather f prime c units, depending on whatever f prime of c is. So that's why g of f prime of x is g prime f of c into f prime of c. So how do I use that? So come back to this function, and suppose I want to differentiate this particular function sine square of x. So suppose somebody asks you to differentiate sine square of x. Okay, so I know sine square of x is sine of x ka whole square. So you assume sine of x as some t square, where t is your sine of x. So what is going to be the differentiation of t square? So the differentiation of t square is going to be 2t, right? So I have already seen that the differentiation of this thing is going to be 2t, and then what you do is you differentiate this t, so into dt by dx. So that's one way to do this in the initial days. Okay, so obviously when I look at this thing, I directly write 2 sine x cos x, because I've had that much of practice, right? I do differentiations on a daily basis, like day in day out. My work is, I work with equations all the time. So I look at sine square, I give you cos square. Like I'm drunk to my throat and I'm sleeping, you wake me up, I'll still say sine square x differentiation to you. But that comes through practice. You are in your initial days. Maybe you are not able to do it right now. So you will use this result to the hilt. That is, you make substitutions. You say sine x is, let's say, t. So what is the differentiation of t square? So either you remember this formula and you can use this formula, or you can do it like this. Okay, so you can say sine x is t and then do all these things. Let's look at the other thing. Let's differentiate sine of x square. So let me call now x square as t. Let me say x square is t. So this just becomes sine of t. So I'm going to differentiate sine of t. So that gives me cos of t. And then I'm going to do dt by dx. Dt by dx is basically differentiation of x square. X square is t. So what is differentiation of x square? So this becomes cos of t into differentiation of x square is 2x. And then you finally substitute t as x square. Don't leave it at t. Okay, t is your substitution. The final answer should be in terms of x, not t. So the final thing becomes 2x cos of x square. And here the final answer is 2 sine x cos x. So you see, the differentiation of these two things is not same. The functions are different, their differentiations are different. So you have to be careful with such complicated functions. So this is your chain rule. So let me give you a little complicated example. So differentiate, let me give it here. Okay, box, right? This differentiate log of sine x. So what is going to be the differentiation of log of sine x?
So cot x.
Yeah. But I'm waiting for others. I want everybody to do it.
Yes, sir, cot x.
So I'll give you 30 seconds. Everybody do this. Cot x, it's basically going to be equal to cos of x by sine x. I want everybody to reach this point. Use these formulae, by the way. That is the reason I've given this question here. You can use these formulae. Although in exam you'll have to remember it, but I'm guessing by that time you would have remembered it. Surely based on the amount of practice we are going to do. Okay, does anybody have a doubt in this one? If you have, this is the time to ask. All right, then I'll move on. Okay, so that's your implicit differentiation, a very, very important rule. We use it a lot. Okay, we are going to use it tremendously, but we don't ever stop to bother about it much. It's there. Now, one of the implications of this implicit function theorem is the inverse function theorem, which we are going to look at. So this thing is important. This has been asked. This proof has been asked in ISI. Okay, so ISI has this proof that prove this thing. So what is this proof? So suppose f is a one-to-one function with some inverse f inverse. So f inverse is the inverse of f. So this b equals to f of a. These are all reasons. These are all just there to establish that f prime exists neatly. Okay, so what we are saying is that the domain of f inverse is the range. Is the range of f. So the range of f is f of a, and that is equals to domain of its inverse, which is fairly straightforward. Okay, so if you have this a and this as b, so f of a, the set f of a should be equal to this set b. Okay? So this is going to be your f, and this is going to be your f inverse. Okay. So assume that f is differentiable at an interior point c on its domain a, and f inverse is differentiable at c. So suppose this is my point c and this is my point f of c. Okay, so I'm saying my function f is differentiable at c, and my inverse function f inverse is differentiable at its image f of c. Okay, so that's what I'm saying. Okay, so that f is differentiable at its starting point here, and f inverse is differentiable at its starting or input point, which is f of c, such that these two are related. So where f of c is an interior point of b, then f prime at c is not equals to 0, and f prime f inverse prime at f of c. F inverse prime at f of c. That is the slope of the inverse function here is going to be equal to the slope reciprocal of the slope of the actual function at c. Okay, so the slope of the inverse function at the image point f of c is reciprocal of this the slope of the original function at c. Another way to write this, some textbooks write this as f prime at c. They just multiply this into f inverse prime at f of c is equals to 1. So this is another way to write it. Okay, so let's look at graphically what he's trying to say. What he's saying graphically is, suppose I take a very simplistic linear function, because linear functions have inverses very straightforwardly. Okay, so linear functions always have inverses. So this is, let's say, my point c, and this is, let's say, my point f of c. Okay, so suppose this line is your line y equals to mx plus c. So what will be the inverse of this line? Can anybody tell me the inverse of this line?
So x minus c upon m.
This is equal to y.
Yes, sir.
Okay, so for everybody, first of all, I should write this k because I don't want to confuse. How do we find inverse? So right now I've written y as a function of x. First you write x as a function of y. So you get mx equals to y minus k. Then you get x equals to y minus k by m. And then you replace x and y. So y equals to x minus k by m. So yeah, you're right. This is the inverse function. Okay. More importantly, this is a line with have I done some mistake? No. Yeah. So 1 by m times of x minus k by m. So the slope for this thing is equals to m, whereas the slope for this thing is 1 by m. When you multiply the two slopes, m into 1 by m, you get 1. So what happens is that when you take the inverse of a line, the x-axis becomes the y-axis and vice versa. That is essentially what I've done here. I rearranged the equation till this point, and then I replaced x with y. So you change x-axis with y-axis. So imagine a piece of paper where you were so able to switch x-axis and y-axis. So if this line basically looked like this right now, a flat line like this, once you flip x and y-axis, it will start looking like a steeper line. Okay. So the slope of this line will become the reciprocal. So a steeper line will become a flatter line and vice versa. The important thing is that the multiplication of the slopes of these two lines will remain one. Now, so if you take any particular graph which looks like this, let's say this is the graph of any one-to-one function. So when this is x and this is y, it would look like this. Now, if you were to convert this as your x-axis and this as your y-axis, the function will start looking like this. This will be the function f inverse of x, if this is your f of x. Okay, start looking at this y-axis, original y-axis as the x-axis. So how's the function going for this y-axis? It looks like this, right? It's going away, but it is concave with respect to y. So it's going away and it's concave with respect to y. So this is the graph of f inverse. So at any point c and f of c, if you draw a tangent here and its slope was m, now for f inverse, f of c is going to be a point in its domain and C is going to be a point in its codomain. And if you draw a tangent here, its slope is going to be 1 by n. This is what he's saying. So as you can see this very clearly for the endpoints, closer to the origin, the slope of this guy is almost 0, whereas closer to the origin, the slope of this guy is almost infinity. Okay, so the multiple becomes equal to 1. So this is the idea. You just change axis, so you can see a curve which is flat becomes steep and vice versa. The slope becomes the reciprocal of what it was earlier. The proof is important because, as I told you, you cannot write this in words. Okay, you cannot draw these figures and everything. You'll get 0 marks if you draw all these figures only. Okay, you'll get marks for this. So what is the proof? So the definition of the inverse is f inverse of f of x is equals to x. So now I apply the chain rule and I differentiate this particular guy. So when I differentiate this using chain rule, the left hand side, the differentiation of left hand side is going to be f inverse prime at f of x into f prime of x. And the differentiation of right hand side is just differentiation of x, which I know is going to be equal to 1. So f inverse prime at f of x will be equal to 1 upon f prime of x. So it's a simple 2-line proof. You write this, you get full marks, 10 marks, 15 marks, whatever marks are there up for grabs, you'll get that. Okay, you don't need to draw graphs. Okay, you don't get extra marks for drawing graphs unless the examiner has asked you to draw graphs. So don't unnecessary clutter. I'll tell you one thing about examiners, they are overworked. Okay, so they don't want to know anything more than what is sufficient. So if it's a 2-line proof, you do it on 2 lines, you get full marks. They don't want you to write Ram Kahani, photos, everything. So this is also important from objective point of view, by the way, because you also get numericals based on this. So you'll see in past years some of the numericals which will be asked on the basis of this inverse value theorem, inverse function theorem. Okay, the next example, we have a function f of x equals to x square, such that f prime at 0 is equals to 0. I know that. Now, f is not invertible on any neighborhood of the origin, since it is not monotone. Okay, so it's not monotone, so it's not differentiable and not one-to-one. So x square, I know, x square looks like this, right? So x square is not a one-to-one function. For 2 values of x, let's say for -1, you get a value 1, for +1, you get a value 1, for -1, you get a value 1. So it's not one-to-one. So you cannot apply inverse function theorem on functions which are not one-to-one. So inverse has to exist. But let's say I define the function only on the positive r. So I'm not looking at the other quadrants. I'm only looking at the first quadrant now. So now the function x square becomes 1-to-1. So now it has a inverse possible. So f prime at x is 2x. Okay, so I know that if f of x equals to x square, then f prime will be equal to 2x. Now f inverse will be equal to under root of y. Right, so if your f of x is equals to x square, then f inverse of x, or let's say y, is going to be under root of y. The inverse of square is root. So the formula for the inverse of the derivative gives that f inverse prime at x square. So if this point is x and this point is x square, so I know that the slope of f prime here is going to be 2x, right? But now what about the inverse? Suppose this was the x-axis and this was the y-axis. So now this function is the inverse of what it was earlier. So f inverse prime at y right? It will now be equal to 1 by 2x, because the slope of this guy is 2x. So the slope of this guy is going to be 1 by 2x. And since x square is equals to y is happening, so x becomes equals to 1 by root y. So this is 1 by 2 root of y. This is exactly the derivative of 1 by root x, which you gave me earlier. I'm not saying that, why am I doing the same thing with the longer method? I'm giving you an example of how to use it. So they might sometimes give you a function for which the derivative is not possible to calculate. So they will divert you in this direction and ask you to find the function and its derivative, and then reciprocal, take the reciprocal and get the differentiation of the inverse function. So this is another similar example. You can look at it on your own. So most of these examples that we are going to look at are going to be functions which we have already established how to find derivatives for. So here we are verifying that the inverse function theorem holds. Okay, now next I want to look at convex and concave functions. But before that, we say that a function is increasing if f prime is positive. Like I told you, f prime is rate of change, right? Rate of change. So if rate of change is positive, you have an increasing function, and it is decreasing if f prime is negative. Okay, if f prime is positive, the function is increasing. If f prime is negative, the function is decreasing. So my question to you is, what about when f prime is equals to 0 happens?
So the function is constant. It's neither increasing nor decreasing.
Okay, so I'll come back to this point. So this is a common misconception which we'll clear now. So these are some nitty-gritties. Okay, so these are some let us call it some exceptional things. You're correct for the most part. We don't call it constant, we call it stationary at that point. Constant would mean the function itself is constant, like a straight line. We use the word stationary to represent what you're saying, but we'll see some examples where it's not true. But for that, to be able to reach there, I first need to establish what is convexity, concavity, and all those things. So I've already established what does it mean for a curve to be convex and concave. I'll reiterate that definition which we looked at in microeconomics. So in microeconomics, I told you that ICs, when is an indifference curve convex? Can anybody tell me the definition for a curve being convex?
So when we take any 2 points on that curve and join the 2 points, the line joining them lies above the curve.
Very good. So this is a definition which just Kanishka told us. It's a definition which holds for multivariate. Yes. Yeah, sorry, there was a power cut here, so the router stopped working. Can you guys hear me?
Yes, sir.
Yes, sir.
All right. So yeah, we were talking about convex functions, and let me know if I'm running it through my phone now through a hotspot. So let me know if there's any disturbance in the quality. Okay, so let me know if you feel any quality problem. I'll reconnect to the router. Anyway, so a curve is yeah. So a curve is convex when what Kanishka said is true, that if you were to link two of its points with the line segment, the line segment lies completely above it. Okay. So imagine a kadai. Okay. So we all have this kadai in our homes. If you drop a spoon in a kadai, the spoon will stick, the entire spoon will lie above the kadai. Right, so a spoon is like a line segment. No matter how you keep the spoon in the kadai, the spoon always lies above the curvature of the kadai. This is essentially because the curvature of the kadai is convex. Okay, I mean, if it were not true, then uh, then maybe parts of the spoon would be going below the kadai. Okay, maybe then you live in a matrix. Okay, if that happens, you are living in a matrix. But that's the idea. Okay, so this definition of line segment lying above the curve is true for multivariate case. Now I want to look at how that relates to differentiation for derivatives for the single variable function. So these definitions that I am looking for convexity and concavity, they only apply for single variable functions. Okay, so that is a condition, single variable functions only. You all know what single variable functions are, right? When there's only one input, it's a single variable function. When there are two inputs, like let's say 2xy, it's a two variable function. In general, greater than one variable is multivariable functions. We could have three variables, x, y, z, and so on. So they're all multivariable. I am only looking at single variable. Later on, we'll look at the results for multivariable, that is in the syllabus, but it's going to be way more complicated than this. Yeah. Okay. So a convex function essentially looks like this. Okay, so a convex function looks like this, a kadai-like structure. So as you can see, the slope here is highly negative. Let's say the slope here is -2. Then I look here, the slope here is -1. The slope here is almost 0, +1, +2, and so on. So the slope is increasing as x increases. Okay, so how do I quantify this with respect to derivatives? So slope is f prime of x. So f prime of x is increasing with x. So f prime x is increasing with x means that the derivative of f prime of x is positive, which means that f double prime is positive. So that's why we say that when f double prime is positive, then we have convex functions. And when it is negative, we have concave functions. So a concave function essentially looks like ulti kadai. Take a kadai and invert it, so that becomes concave. Okay, so one thing I find it very crucial to remember the difference between concave convex is that when you have a concave function, it's like if you're standing here, it looks like a cave on you. You're standing in a cave. Okay, so maybe you are one of those person who gets confused between these definitions. I always do. So that's how I remember it now. Anyway, as you can see, it is highly positive, less positive, negative, and increasingly negative. So f prime reduces with x. So f double prime, which is d by dx of f prime of x, this has to be negative. Okay, so this is your concave functions. Okay. Let me just be back. There's somebody at the door. Give me a minute. Okay. Sorry. So, so that's about concavity and convexity of these functions. So I've already established increasing and decreasing. So a function like this is increasing convex, this is increasing concave, decreasing convex, decreasing concave. So if I look at an example, you have this function. So we have to find areas where it is going to be increasing, decreasing, and convex, concave. So let's do this example. F of x equals to x square minus 2x plus 2. So first I look at f prime of x. So f prime of x is equals to 2x minus 2. So let me ask this question to, who do I ask this question to? Who hasn't participated today? Yeah, you actually.
Yes, sir.
Yeah. So for what values of x is f prime going to be positive and when is it going to be negative?
So when x equals to 0 or less than 0, it's going to be negative.
No. No. Look at this function, 2x minus 2. When is it going to be positive?
So I was telling for negative.
Okay. Tell me for negative. When is it
Sir,
going to be negative?
smaller, equal to or smaller than 0, sorry. Or equal to
So you're
0 even.
saying that at x equals to half, this function is positive?
Sir, I'm saying when x is smaller than or equal to 0, the function will be negative.
Okay, fine. Accepted for x less than 0. Okay. What about positive then?
Sir, x greater than 1.
So what happens between 0 and 1? What happens at x equals to half? Are you sitting with a notebook, you actually?
Yes, sir. It will be negative.
So why haven't you counted that here?
Oh, sorry, sir.
You have to write it like this. So this is 2x
Yes.
less than 2. So
Sorry,
x
sir.
less than 1. What are you doing? Don't lie to me that you're sitting with a notebook, because if you would have, then you would have gotten here very easily. Okay? If you're sitting with a notebook, write on it. Don't stare at it. So x should be less than 1 for negative. So basically this function on the real number line to the right of 1, it's going to be increasing. And to the left of 1, it's going to be decreasing. Okay, so it's going to be an increasing function to the right of 1, and it's going to be decreasing to the left of 1. Now, what about concavity? So if I again differentiate this f double prime of x, yeah, so f double prime of x is going to be equal to 2, which is always positive, which means that the function is convex. Okay, so the function is going to be convex decreasing here and then convex increasing here. So basically it looks something like this, a u-shaped function. At 1, it achieves its minima. So the only way to draw it would be like this, right? It will be a u-shaped function. Then it is always convex, decreasing here and increasing here. Okay. All right. So it is basically going to be about finding these simple things. So let us look at a few examples now. And implicit differentiation, I want to do implicit differentiation. That is not necessary right now. I want to do some problems. So linear approximation is not necessary. Okay, cool. So anyway, derivatives will not be over in one chapter. So in the problem sets, you will find this very interesting thing called okay, this differentiation you can handle on your own. Obviously, I expect you to. So please do this differentiation exercise first, and then we'll lead to curve sketching. So you have to first, so there's going to be a lot of work for you guys this week because this is a huge problem set. So let me talk about this curve sketching. So how this works. So the aim of this problem set is to learn how to sketch curves of different graphs, different functions. So what this will do is that it will train you in a step-by-step manner. So it's not going to directly say, okay, obviously when I look at a function, I cannot draw its graph directly. So we are going to learn it in a step-by-step manner. So let us look at this function 3x to power 4 minus 8x cubed plus 10. I'll also, okay, this also asks you local maximum minimas. Let me also cover that topic. Let me do optimization. I'll cover these topics later on because I want to do everything related to this problem set so that I can give it to you as homework. Let's do single variable optimization. So optimization is, as I told you in the starting, this is going to be the aim with which we are learning this particular topic. We want to learn how to do optimization. So the points in the domain of a function where it reaches its largest and smallest values are referred to as maximum or minimum. If we do not need to bother about the distinction between maximum and minimum, they are together called the extreme points. So suppose the points where it reaches its maximum are called max points. The points where it reaches its minimum are called, let's say, min points. So the union of these 2 points, the set of points, is going to be the set of extreme points. First, we need to develop the concept of extreme values. So what are extreme values? So suppose a function f is defined on the set A, and f has a global or absolute maximum at an interior point C, at a point C in the domain if the functional value at C is greater than or equal to the functional value at all the other points. Okay, so this is the definition for a global maximum. So in the case of Earth, if you're looking at the altitude function at different points, then the point at which the altitude gets maximum is going to be the Everest point, the point of Everest. Okay, so the peak, Everest peak. So the point C here is going to be Everest peak. So the height at Everest peak is greater than equals to height at any other point on the surface of the Earth. And then there's a weaker concept of a local maximum. So a function has a local maximum at some point C if there exists a neighborhood around C such that f of C is the largest value in this neighborhood. So suppose I have a function which looks like this. Okay, this is the entirety of the function. It starts from here, it ends here. So this point C1, C2, C3. C2 is a global maximum. Now C1 is not a global maximum because the functional value at C1 is lower than C2, but it is a local maximum because you can construct a neighborhood around C such that in this neighborhood, the highest value the function takes is at C. Okay, so what are the total number of local maximas of this function?
Three.
Three. Very good, Vinay. Okay, C1, C3 are local maximum. C2 is also a local maximum. So it is local and global maximum. Okay, so this is one mistake that you might do sometime, that global maximum is also a local maximum. In its vicinity, it's still the highest point. It's another matter that it's the highest point over the entire domain, but it is also a local maximum. So the number of local maxima are going to be 3. So the set of local maxima is always going to be a superset of global maxima. Or if you don't know supersets, then the set of global maxima are going to be a subset of local maxima. Okay, they can also be equal. They can also be equal. If you have a function which looks like this, then this is the only local and global maximum. Okay, so in this bell-shaped type of curve, the set of local maximum is the same as set of global maximum. Okay. Now, the function f has a minimum if the functional value at C is lower than every other point. So now you can imagine a function which, suppose for the same function here, right? So suppose this point, okay, let me draw a new function. That would be better. Okay, so suppose I draw a curve which looks like this. Okay, so it starts from here and it ends here. So this is a local minima, this is a local minima, and this is a local minima as well. Okay, it's on the end, but it is still a local minima. Okay, doesn't matter that it's on the boundary of the domain. Suppose this is my starting point A and this is my end point B, and the function is defined on A to B. It is still defined on B, right? So, and in its vicinity, if you take any subset of the domain here, this point is still the minima. So this point C1, this point C2, and this point C3, they are all, and this point B, they are all local minima. So the set of local minima are going to be C1, C2, P. Whereas you know that this point from the figure, this point is the lowest. So this is the global minima. So the aim is to find these values. Okay, so the aim is to find these values. So how do I find these values? Okay, so there's this important theorem, which is called the Weierstrass's theorem. So the Weierstrass's theorem says that a continuous function on a compact set has both a maxima and a minima. This is a theorem which talks about existence. We are looking for a maxima and a minima, but it is not always necessary that every function has a maxima and a minima. For example, if you define a function f of x equals to x on the set 0 to 1. So this function defined on this set, it does not have a maxima or minima. X equals to 0 is not a minima because 0 is not even in the domain. You can never reach 0. Similarly, x equals to 1 is not a maxima because you never reach 1. The problem is that this set is not compact. So the question is, what is a compact set? So compact set is a closed and bounded set. A closed and bounded set is called compact. Okay. So it should be closed and it should be bounded. So let me give you some options and you tell me which of these sets are closed and bounded. So the set -1 to 1, 0 to infinity, 0 to infinity, negative infinity to infinity, and -3 to 2. Which of these sets are, first of all, closed? Let us talk about which of these sets are closed.
A.
A is
A.
closed. Fine. Is B closed?
No, sir.
Why not?
So it's just closed from one side, but the other side it's open. So
What was the definition for closed sets?
So it can be, so since the real numbers are both open and closed, so if we talk about infinity,
I'm asking you the definition. Does anybody remember the definition of a closed set? It's absolutely important for you guys to remember the definition for closed sets. So those of you who have attended the lecture, can anybody remember the definition for a closed set? We did 2 definitions for closed set.
so when we take any point, if we take 0 and construct any neighborhood around it, so it should lie inside the set, but since at 0, when we construct any neighborhood, it will lie outside the given set, so it's not
Okay, so you're
open.
talking about the definition for an open set. I'm asking you the definition for a closed set. You can build a definition for a closed set using an open set. There was some connection between closed and open sets, if you might remember. Okay, so the idea is that the simpler definition is a set A is closed if A complement is open. Okay, so what is the complement of this set?
-infinity to 0 open set.
Okay, now in this thing, the definition that you are talking about works. All right. So the definition for an open set is that, let me type this, that would be better. So set A is open if for any x in A, there exists a neighborhood U in A such that X lies in U. Okay, so this is the definition. For any a set is open if for any point in the set there you can construct a neighborhood around that point which lies in U. So the set negative infinity to 0 is open because you take any point in this set, you can construct a neighborhood around it which lies completely inside it. So 0 point is not included. So you'll not talk about constructing a neighborhood around 0. That's not allowed. Okay, so you are talking about points inside the set. So here this set verifies this property. So this set is open, which implies that its complement is closed. So yeah, this is closed. Okay. Is this thing closed?
Yes, sir.
This is closed because I told you two sets, R and phi. They are both closed and open. Okay, so these are the only two sets which satisfy this property. This thing, is it closed?
No, sir.
No. Is it open? Is this set open?
No, sir.
No. Sets are not doors. This was a statement I made. It's not like if it is not closed, it is open. So door is, you see, doors are closed or open. So it's not that sets are always going to be one or the other. So in the set of all sets, this is going to be the set of open sets, and this is going to be the set of closed sets, and wherein here you have your R and phi. This is your closed, other closed sets. These are the open sets. This is in the entire reals, in the set of all subsets of real numbers. And then there are a bunch of other sets which are neither open or closed, like this one. Okay, so this one is neither open or not closed. Okay, let me add one more thing here. The set singleton point 4, is this open or closed?
So closed.
Closed, yeah, closed. Because if you take its reciprocal, it will satisfy this definition of open set. Okay, so it is closed. Now let's talk about boundedness. Boundedness is easy to check. You should not see infinity or negative infinity. So I know that this is bounded, this is not bounded, this is not bounded, this is bounded, this is bounded. So when I talk about closed and bounded, it's going to be this set and it's going to be this set. These are the only two sets which are both closed and bounded. So these two sets are going to be called compact sets. So a very important definition, closed and bounded sets are called compact sets. Okay, it's a very important definition for you guys to remember. I'll add it in the notes as well. In an earlier version, it was there. I think I have accidentally uploaded a wrong version. So that's why it's not available. So it should be there. I had added this. So I'll search for that new version and upload it. In the meanwhile, these are the things which are missing. So, so the Weierstrass's theorem says that a continuous function on a compact set has both a maxima and a minima. Okay. So when we talked in microeconomics about when we talked about preferences being represented as utility functions, I talked about three things that preferences need to obey. Transitivity, then continuity and completeness. Now, this continuity is something which comes into the picture. If preferences are continuous, then utility function is also continuous. Okay. Now, utility functions being continuous, no, sorry. Okay, no, sorry. That was continuity of preferences. Sorry, I got confused. Utility functions can be discontinuous. Forget preferences and these three things. Suppose you have a utility function that is continuous. Let's say you have a utility function that is continuous. Okay. Utility function that is continuous. What is a continuous utility function? I know continuity for single variable. For multivariable, we'll do continuity. But the idea is most functions that you will get are going to be continuous. Okay, so most types of functions that we deal with are going to be continuous. So you'll not even have to check for continuous function. So first we take a utility function that is continuous. Second, we take the budget set. So we talked about budget sets. So if this is X and Y, the budget line is the line which satisfies Px times X plus Py times Y is equals to your income. Everything inside this line, below this line, is what we call as the budget set. Now, this budget set is a compact set. My one-dimensional theorem definitions will not apply so easily on this multi-dimensional set because this is a set in X and Y. But you can see it is bounded because you can draw a circle around it. Okay, so the idea for a set being bounded is if you can encapsulate a set in some circle of a finite radius, then it is going to be bounded. So it is definitely bounded. And it is closed. The definition for closed is that any sequence in the set ends at a point in the set. So you take any sequence of points here. So this sequence, as long as it lies inside the set, its limit point also lies on the set. Okay, so if you take the budget line as not approachable, if you take the budget set, if you define the budget set as Pxx plus Pyy less than I, then this set is no longer closed. Because of this equality that people can consume their entire income, what happens is that this set becomes closed. Okay, these are important things because they can ask you in an interview, they can ask you in a theoretical question that what happens if you remove this equality? What if consumers are forced to consume strictly inside their budget line, that they cannot consume their entire income? If you do that, what happens is that the budget set is no longer closed, and by that reason, budget set is no longer compact. So since we have this equality here, this ensures that budget set is compact. The existence of budget itself applies the condition of continuity, and the availability of the option to consume your entire income gives you the property of closeness. So now that you have closed and bounded budget set, it becomes compact. Now utility function is continuous, budget set is compact. So these 1 and 2, they imply that Umax exists. So I'm looking for utility maximization. All the first chapter that we did was maximize utility. But we never stopped to ask, like, what if the utility maxima does not even exist? Can that happen? Okay, so that can happen. If any of these conditions is not met, that can also happen. So here we are certain that utility maxima exists because the budget set is compact. So now that first thing, whenever you are being asked about a maxima minima, the first thing is that we look at if the function is closed and bounded. So the domain is compact or not. if the domain is compact or not, and the function is continuous or not. If that is true, then we move to the next step, and there we try to find the critical points and boundary points. So what are critical and boundary points? So a function at which the function, the point at which the function is not differentiable, or f prime is 0, is called a critical point. So critical points are points where function is non-differentiable or its derivative is 0. And then we have already looked at what boundary points are. So if f is defined on 0 to 1, okay, on 0 to 1, if f is defined, then the boundary points are going to be 0 and 1. Critical points are going to be points where f prime is not defined or if f prime is 0. So first we focus on these two types of points. Next, we try to look for an optimum. So the next thing is, let's look at this example of a function f, which is defined as x from -1 to 0. So between -1 and 0, this function looks like this, and between 0 and 1, it looks like this. So x equals to 0 is a critical point because the function is not differentiable here. You see, it has a kink. Okay, its slope is different here, its slope is different here, so it is not differentiable. A function is differentiable if it is smooth, right? If f prime exists. So if you look at f prime value for x greater than 0 will be equal to 1, and f prime value for x less than 0 is equals to 2. So f prime at 0 does not exist. So this function is not differentiable. F prime is not continuous, right? F prime is not continuous. So this function is non-differentiable at 0. Now, the global maximum, but this point, even though it is an extrema, this is an extreme point going by the definition of extreme points, because I defined extreme points as points where f prime is 0 or f prime is non-existent. So by that logic, I know that this is an extreme point, but that does not mean that it has to be an optima. As you can see from this function, this is neither a maxima. This is the minima and this is the maxima. This point is neither. So just because it's an extreme point does not imply that it's going to be a maxima or minima. Okay, so we are going to first collect all the extreme points, and then we'll see which of these are going to be maximas or minimas. Next, look at the function x cube. So this brings us to the thing I was talking about earlier. So I think Kanishka told me that if f prime is equals to 0, then the function becomes stationary, that it is neither a maxima or a minima. Okay. So let us look at that it becomes, the function becomes stationary, that it is neither increasing nor decreasing. Okay, so let's test this argument here. This is a very common misconception that people have, that if f prime becomes 0, the function stops increasing. So for x cube, I know that for f of x equals to x cube, I know that f prime equals to 3x square, which is 0 at x equals to 0. So I would like to think that this function, maybe it achieves some sort of maxima or minima here. But if I look at the graph of x cube, it looks like this. This is what the graph of x cube looks like. So the question is x equals to 0 a maxima? The answer is no, because if you construct any neighborhood around here, you have points to the right at which function is higher than what it is at 0. At 0, this function is 0, right? So f of 0 is 0. but f at any value h greater than 0 is going to be h cube, which is positive. So it is clearly not a maxima. So that brings me to the next question. Is x equals to 0 a minimum? The answer is again no, because now you look at points to the left of 0, you know that the functional value is lower than this. So it's neither a maxima nor a minima. The definition of a maxima minima is that in some vicinity, it should be either the max per thing or it should be the lowest thing. Neither of that is happening here. So this function is neither a maxima nor a minima. Which then brings me to the question, is f stationary? Okay, the answer is again no. The function is increasing at x equals to 0. Okay, the function is increasing at x equals to 0 because the actual definition of an increasing function is that if you so the idea of an increasing function is that if you are going to increase the value of x, it's going to increase the functional value. Okay, so the definition of a functional function being increasing at any point is that limit a function f is increasing at c if limit h tending to 0 plus f of c plus h is greater than f of c, and limit h tending to 0 plus f of c minus h is less than f of c. So slightly to the left of c, the functional value should be lower. Slightly to the right, the functional value should be higher. And that is in fact what's happening here. You go slightly to the left, the functional values are lower. You go slightly to the right, the functional values are higher. So this function is in fact increasing at c. It's not stationary. So this is the actual definition for an increasing function. So this function x cube, is increasing at x equals to 0. It's not stationary. So what's happening is that x equals to 0 is actually an inflection point. So x equals to 0 is actually an inflection point. So we look at how to identify inflection points and all those things. Right now, I don't think I'll be able to wrap this entire thing up. So no point me trying to do that. There's a lot of things left to do, which I can't wrap up in 10 minutes. You guys are tired, I'm tired. So let's forget curve sketching for the time being. Let's just try to do this one problem set, which I have given you. So your homework for today or this week rather, it is going to be that you have to do this differentiation PDF only, the problem set on differentiation. I don't want you to do too much. Okay, I've already edited the other parts. Okay, so 16 questions is sufficient. So do this much 16 questions. Maybe you can leave this 10th question. Okay, it is too complicated, so you can leave 10th question, do the remaining ones. Tangent lines, I don't think it's relevant anymore. They don't ask tangents. I will take a doubt session on math, maybe Tuesday, in which I'll try to teach about tangents. If you attend it, maybe you can do it. These exams have not asked tangency for the last 10 years at least. So I don't think if it's important. If you're free, feel free to attend that lecture. I'll put it as a doubt session on differentiation. I'll do some basics of differentiation for those of you who might have problems. So before that, I want you guys to try this problem set so that we know what the problems are. Most of you must be good at it, I'm assuming. Some of you might have become a little rusty, so we'll focus on that because it's a very important topic. And you can read this document on differentiation here, not in problem sets. Before that, in lecture notes, there's a document on differentiation if you want to read before the doubt session, and then you can ask doubts from this particular topic as well. Okay. Tomorrow I might not be able to take a lecture. I will not be, actually. I don't want to keep it uncertain, because I have to go out for a wedding, and although it's a small affair, it's an afternoon wedding, but I never know. We never know how it can get late. So I want to take a extra class. So does Monday work for all of you? Monday evening, 4 to 6. Does anybody have an issue with Monday evenings?
Can we keep it like after 5 because I have classes till 5?
Okay, which day do you not have class at 4? I want to take a day in which you're free, because then you are relatively fresh.
So
Kritika.
just a minute, I'll just check.
All right, fine. So let's tentatively keep it at 6 o'clock on Monday, unless we can find. We'll chat about it on the group, because there are some
So we
of
can
you who
have
are
it on
not.
Tuesday or Wednesday.
You can have it on Wednesday 4 o'clock.
Yes, sir.
Everybody okay with Wednesday 4 o'clock?
Excuse me,
Everybody here?
sir.
Yeah.
But we have a continuous class from 11:30 to 3:30 on Wednesdays.
And what about Tuesday? Are you okay with Tuesday?
Yes, sir. We can have it on Tuesday in that case, or maybe Thursday if it works with everyone.
No, that doesn't work for Kritika. So Tuesday works
Okay.
for most of you. The others, Tuesday evening. Nobody has an issue. Okay, I'll post this tentative time Tuesday evening 4 o'clock on the chat. Maybe if nobody else has an issue, we'll keep it Tuesday 4 o'clock. Otherwise, we'll have to look for some day later in the evening. Okay. All right. So I'll stop here. I'll see you guys on Tuesday tentatively, and we have a doubt session. Okay. All right. Let me stop.
Thank you, sir.
Sure.
Thank you, sir.
Welcome. Okay. Bye, guys.